Yeah, so example number 2. So if you look at this one right here, what would you guys say is like the overall description of the integrand? Like what operation is it?
A product.
It's clearly a product, right? But one of the two factors is composite, and so that should hopefully bring to your mind, well, maybe this would be a Timmy messed up the chain rule, or in this case, we're going to do a U substitution. So if you are going to set up U substitution, if you watch the video, or if you just remember, we always want to make the U a very particular part of the integrand. Do you remember which part? The inside of the composite is right. So in this case, U would be 2x minus 1. Bless you. And then the other thing we want to set up, of course, is our du. So what would du be here? 2dx. Okay. So at this point, we can substitute, partially at least. I would say that our substitution would be integral of x times the square root of u times du over 2. We're trying to convert all of the x's over to be u in some form or another. And I'd say that's where we are. Are you guys all okay with the du over 2? I didn't say too much about that. Divide both sides by 2, dx equals du over 2. Okay. So I would, in the next step, I'm definitely going to get the 1/2 out of there, like the over 2 part. I'll get that out of the integrand. But we still have to be honest and say that we have an issue right there, don't we? That x needs to be converted over to be some kind of a u. So do you guys remember, this is kind of the more challenging u substitution variety. What do we do to get that x out of there, replace it with some expression in terms of u?
You take the u equals 2x minus 1 and solve for x.
That is right. Good job. So let's see here. It'd be u plus 1 over 2 is equal to x. So I can go back over here now, and I can actually finish my substitution. So it's going to be integral of u plus 1 over 2 times u to the 1/2 times du over 2. So I think I'm going to, instead of taking a 1/2 out, I'm going to take a 1/4 out, right? Because I've got 2 over 2's. And so I'm going to make this 1/4. And I'm not going to write the next thing yet. Well, actually, I think I will. So I'll write u plus 1 times u to the 1/2 du. We've converted everything over to u's now, right? But we are definitely not out of the woods yet, because what is the integrand? It's a product. And so here would be where you could say, oh, cool, it's a product. Maybe I'll just think about the whole Timmy messed up the chain rule thing. But if you think about it, what's the derivative of the inside? It's kind of a 1, sort of, right? Does that match? It doesn't match the outside at all, and it's not something we can fix. And so I would say, in general, if we can avoid having a product, just like if we can avoid having a quotient, we should try to avoid it. So how do I take this from being a product to something that's not a product? And that's the step that I find that most people with good intentions and good skills forget. At this point, they maybe get stuck, or they do something kind of crazy. They forget you can just distribute in this situation. So it'd be 1/4 integral u to the 3/2 plus u to the 1/2 du. And now this can be relatively easily anti-differentiated. So let's do that. So let's see here. It's going to be 1/4 times 2/5 u to the 5/2 plus 1/4 times 2/3 u to the 3/2 plus c. I'm actually going to break a little rule here and go up now. No, I'm not. I'm going to keep going to the right. I got room. Okay, so this gives me then 1/10. I'm going to plug back in here too. 2x minus 1 to the 5/2 plus 1/6. 2x minus 1 to the 3/2 plus c. So that'd be it. Oh, and we kind of lost there, didn't we? You guys okay? You don't see my plus c. It's really there, I promise. Do you see how this is one where u substitution is kind of the way you got to go? I don't see us like looking at it and be like, oh, this is obviously the two-term pattern where you multiply and no, I don't think so, right? And so being able to do u substitution here would be key. And just a reminder that there are going to be times when you're asked a question where you're only asked to kind of go halfway through u substitution. I think there might be an example coming up, or there's at least one in the extra practice. And so we want to be able to do u substitution for sure. Okay, do you have any questions before I kind of turn you loose a little bit? Okay, let's do number 3 here. Number 3 is a little more challenging. Would it be fair to say that number 3 is not just a composite? Isn't it like a double composite? It's something inside something, and then that whole something is inside something else. So if you guys would take a look at number 3, try to do u substitution with it. You could do Timmy messed up the chain rule. It's very doable here, but perhaps u substitution is the better method. So give it a shot. Let's put it like this. This is like the more composite factor, right? It's got more going on. It's like something inside something inside something. And it's true that the other factor is also composite. I would work with, you really have to work with one that's like the more complicated composite. And so if we were to maybe rewrite it a little bit, we could write integral of sine of 3x squared, like in parentheses squared, times cosine of 3x dx. And when you do it like this, and maybe if we put parentheses here and here, when you do it like this, you can more clearly see like the most inside function. Like last year I would have called it the tiny box. So like what's the tiniest box?
3x.
The 3x is the tiny box. We're still looking at the left factor. Which box is kind of like the medium-sized box? Sine of whatever, right? Sine of 3x in this case. Wouldn't the biggest box be something squared? Okay. So whenever you have these situations where you've got, a box inside a box, and then that whole thing is inside another box, what you want to do is you want to set up your u, because like the u is supposed to be the inside function, right? So couldn't you by all rights say that the u is 3x? Isn't 3x an inside box? But I think the better way is to make the u sine of 3x. Make the u the middle-sized box. I think that'll chew up enough of the details or it'll make it a little bit easier for you. So I would start there. So u equals sine of 3x. And then from there you build out your du and try to substitute. So let you just have another couple of minutes here to try to hash that out. And if you can't, that's fine. I'll help you, but see if you can do some of that on your own. We'd get 1/3 times 1/3 u cubed plus c. So that would give us 1/9. And I will then take my u that I substituted with and just plug it back in for the u. So it would be 1/3 times sine cubed of 3x plus c. And we're done. Obviously, if you have any doubts about the validity or truth of that, you could always test it out by doing a derivative, doing the chain rule. And I think you'd see that when you did that chain rule, the right things would cancel out and simplify, and we'd end up with the same thing as our original integrand. Okay, so we good?
Yep.
I'm seeing calm faces. It's a good thing. Sean, yeah? Looked like you eventually got there, right? Awesome. Fantastic. Okay, so let's switch gears a little bit. You probably noticed that examples 1 and 2 and 3, they were all antiderivatives, right? They were all indefinite integrals. And so this same process can be applied to definite integrals. With definite integrals, we actually call it a little bit of a different name, although it doesn't have to be called this. Your book calls it change of variable. But that's what we've been doing, right? Haven't we been changing the variables from x's to u's? That's all this is. So you could call u substitution, change of variable. It's all the same thing. They apply to both antiderivatives as well as definite integrals. So don't feel like this is this whole different thing. It really is the same thing. They call it something slightly different in your book. So I'm honoring that. Perhaps I shouldn't, but it is really all the same stuff. Okay, so notice here that instead of just an antiderivative, we got limits from 0 to 1 on the integral. And so we're going to deal with this. We just have to deal with them. That's it. It's not really a new technique. We just got to figure out a way to deal with them. So let's just work this one together. You guys tell me, what should my u be as I seek to substitute here? X squared plus 1. Using the inside there makes sense. So if that's our u, then our du now has to be 2x dx. Okay, so I'm going to substitute, and I'm going to be really careful about this. I am going to just leave the limits off for the moment. I'll deal with those later. I'm just going to leave those limits off because I don't want to confuse myself. The reason being, those two limits are x equals 0 to x equals 1. It's not anything equals 0 to anything equals 1. How do I know that? How do I know that those 0 and 1 are in terms of x? Why do I kind of have to assume that? Because it doesn't really say, does it? Could be y. If we're talking about 3 space, it could be z. How do I know? Well, I think we have to assume, right? Like, why should I feel comfortable assuming? How do I know that the 0 and the 1, the two numbers that I have highlighted up there, how do I know that those are in terms of x? Like it's x equals 0 to x equals 1, not some other variable. Yeah, the dx is a big indicator, and then everything in the integrand is all x's. And so if I was going to write a good question and I intended the 0 and the 1 to be in terms of something else, the fact that all of those are in terms of x, I'd have to indicate it. I'd have to say like y equals 0 to y equals 1, or use, or whatever. I'd have to indicate that. I think it'd be unreasonable to assume otherwise. So if those really are in terms of x, I'm going to have to convert those as well. So I'm not going to write them yet. I'm just going to write integral of, I would have u cubed based on the substitution we set up. I would still have an x right there. The dx, let's see here, would be du over 2x is equal to dx. So I'd replace the dx with du over 2x. The x's would then cancel, which is what we were hoping for. And I end up with 1/2 times the integral of u cubed du. Now, let's deal with the limits. The old low limit was 0. How do I get the new high limit? Yeah, plug it into this equation, right? Because that's the only one I've got that relates u with x. So that's really the only way I have to convert from x to u or u to x. So I would say u equals 0 squared plus 1. Also known as 1. So my new low limit down here will be 1. My new high limit would be u equals 1 squared plus 1, which is 2. Okay, so we're going to take this all the way through here, but what I want to point out, this is where there's points of confusion at times, because when we have an antiderivative like we did in the previous questions, wouldn't we, just follow with me here for a second, if we were doing the old question, like we did in examples 2 and 3, wouldn't I find an antiderivative and then plug in the x squared plus 1 back in for the u? Yes? Does that make sense? We will not be doing that here. What we've done is we've converted, well, let me put it like this. Isn't the answer to an indefinite integral a family of functions? What's the answer to a definite integral? So whether the number came from a bunch of x's or whether the number came from a bunch of u's, as long as my substitution was valid, does it really matter that it came from x's or u's? It really doesn't. So I'm going to leave everything in terms of u and just finish this way. I'll point out a common error here in just a second. So here's what we would do. We would go 1/2. The antiderivative of u cubed is 1/4 u to the 4th. Evaluated from 1 to 2. So I'll simplify this a little bit. And let me point out the error. Here's what a lot of people will do. They will say, so this is bad. Please don't write this down. What I'm about to write. Don't write this down. They'll say, oh, I know what u is. It's x squared plus 1. I can see that plainly up there. Now I'll evaluate from 1 to 2. What is the problem with that? Yeah, remember we converted these over to u's, didn't we? And so now I've got x's for inputs, but I'm about to plug u's in for them. That's going to create a problem. So we do not do this. We just leave it in terms of u. There's no substitution here at all, as far as back substitution goes. Make sense? Maybe more importantly, can you see why someone who's pretty smart and pretty much knows what they're doing could still do that? So just be aware. Okay, so to finish this off, it would be 1/8 times 2 to the 4th minus 1/8 times 1 to the 4th. So let's see here. 2 to the 4th is 16 over 8 is 2. I got 2 minus 1/8. So I'm coming up with 15/8. You guys agree with that? 1 and 7/8 if you are of the mixed number persuasion, which please don't be. Just leave it as 15/8. Okay, we good? Okay, so the next question, like this process you'll want to be able to do, for sure. But the next question is, for some folks, ends up being sort of an unexpected question, or at the very least a confusing question. If your name is not Sean, you probably saw this on the AP test last year. You definitely saw it at least once in the notes in some form, maybe an extra practice or something. Let's see if you can handle this. This is basically how, like, the question is, can you set up U substitution? That's essentially what this is about. So give it a shot, see how it goes. I guess my approach to these is not to like do it all in my head and try to pick the right answer. I'm going to go through the process. And so if I was going to go through the process here and set up my U for this particular integrand, what would my U have to be? X cubed minus 1, I agree. So that's set up there. And my du that would then have to be 3x squared dx. So when I go to substitute, I would write integral of u to the 7th times x squared. And I'll use my du equals 3x squared dx to write du over 3x squared for that substitution. Of course, the x squareds cancel out, which is what we were hoping for. And I end up with 1/3 integral of u to the 7th du. And it might be at this point that we say, oh, okay, so it's got to be either b or c, right? We don't know that that's for sure true, but that seems, I'm encouraged that something's up there that looks sort of like what I've got. The main thing that's remaining here is how do we deal with the limits of integration? The old limits of integration, of course, were 1 and 2. And this is where someone who's like most of the way there would make a mistake and circle b, right? They would just say, oh, 1 to 2, I see it. That was there before, it's still there, we're good. But they've forgotten that they need to convert their limits of integration over to u's as well. So if they were 1 and 2 before, we're just going to use this. So u, the new low limit, would be 1 cubed minus 1, which is 0. And at this point, we could probably pick the answer C, but let's just make sure we're all good as far as getting everything correct. The new high limit would be u equals 2 cubed minus 1, which is 7. So I think we'd have to go with C for an answer. Does it seem logical? Good? Yes? Lenny, you still think you missed that one last year? No. Okay. You have a better shot this year? Yeah. A little better shot? Okay, that's good. All right. Well, let's go ahead and move forward here. We're gonna talk about some evens and odds, and we'll do a little trapezoids, and that'll probably be about our time, and we'll be done with chapter 4. Okay. So this is calling on some old pre-calc stuff. Even functions are symmetric with respect to the y-axis. Yeah. Even axis. Hey, you know, we all knew what you meant. We speak your language. Okay, so an example of that would be the parabola y equals negative x squared plus 4. So here's my attempt at drawing that parabola. It's going to have y-intercepts, or x-intercepts there and there. Oh, I'm going with that one. That one's pretty good. Okay, so you can see that that graph does have y-axis symmetry, split right down the middle by the y-axis. My drawing is actually decent enough you might be able to tell that. So if you were told that you had an even function, maybe you knew that it was this one, or maybe you didn't know what it was, you just knew that it was even, and you were told that the integral from negative 1 to 1 is 22/3. So we're talking about from right here to right there, essentially talking about this area. We're told that that is 22/3. And then they went on to ask us, what is the integral just from 0 to 1, which would be this over here. What would you say? half that, which is 11/3. There we go. Bless you. I was wondering, McKenna, if somebody was going to just say half that, which, yes, that's true. Half of 22/3 is 11/3. Or you could have said 22/6, right? Same thing. So the general principle is if f is an even function, then the integral from negative a to a is equal to double the integral from 0 to a. Of course, you could rewrite this a little bit. You could say 1/2 of the integral from negative a to a of f of x dx is equal to the integral from 0 to a. And that's more the principle that we just used, saying, hey, if you know the whole thing and you want to know half of it, just multiply the whole thing by half. Obviously, the same relationship, just written slightly different from a different perspective. If we have time today, we'll talk about this. Do you guys realize that cosine is an even function? Right? Yeah. And I don't know if you remember this from back in pre-calc, but if you look at a polynomial, if a polynomial is an even function, then all of its exponents will be even, right? Yeah. So like if you had f of x equals x to the 6th plus x to the 4th plus x squared plus 8, every single exponent, including the last one, 8x to the 0, right, follows the even pattern. So that would be an even function. If you had like f of x equals x to the 8th plus x to the 6th plus x to the 4th plus x, now it's neither, right? Because it doesn't follow the all even exponent pattern. If we have time at the end, we'll talk about why cosine is even and try to make a connection with that. Okay, let's take a look at odd functions. Odd functions are symmetrical, not with respect to the y-axis, but with respect to? Good, I couldn't mess you up. I was just going to see if you were going to say x-axis. So origin is correct. What am I thinking? I can't fool you guys. So an example of this would be g of x equals sine of x. So if we were to graph this, I will do my best here. That's going to be a good graph. Woohoo! I'm happy about that. I don't often get it right the first time. It's pretty close. I mean, my right x-intercept's probably a little too big, but I'm not going to worry about it. This is an example of origin symmetry, where if you mirrored any point on the graph across the y and the x-axis in sequence, then you would get an image there, right? You mirrored across both axes, or you could say across the line y equals x. So if I told you that the integral from 0 to pi was 2, I'm essentially talking about this area right here when I say that, like that. Then what would be the integral from negative pi to pi? Nope. It would be 0. We know why you did that, right? What question would it have to be if the answer was 4? No. So what if you had the same function, same everything, but I changed the question so that the answer would be something having to do with absolute value, or if I said what is the total area between the x-axis and the curve, something like that, then 4 would be the answer, right? But this just said what's the integral, so you'd say that while this being, this would integrate as a positive 2, this would integrate as a negative 2, and as you accumulate those, that obviously would add up to be 0. So a general principle, if g is an odd function, then the integral from negative a to a is 0. Right there. Okay, and there's like some slight manipulations you could do with that, kind of like what we saw with the even functions. So just like before, you guys remember probably that if you have a polynomial, and with a polynomial, if all of the exponents are odd, then it's an odd function, right? Just like all the exponents are even, it's an even function. Sine is odd, right? You can see that from the graph perhaps. How does that work with the whole exponent thing? Is there a connection? If we have time today, I'll show it to you. I eventually will definitely show it to you, but perhaps today I can show you at the very end. Okay, so our final topic in chapter 4 is trapezoids. So approximation is a necessary skill, necessary in the fact that approximation always makes something easier. And so at times we're going to use rectangles, with left sums or midpoint sums or right sums or whatever. But perhaps a better method would be trapezoids. Why are trapezoids perhaps better at times? What does a trapezoid have that a rectangle doesn't? slanty side,
Yeah.
diagonal side or something like that. Yeah. With a rectangle, it's all right angles, but with a trapezoid, you can have one of them being sort of angled. So if we were to look at something like this, you could use a trapezoid. You can see how that trapezoid there and that one there, pretty good approximation. It's better than using a rectangle. I tried to make all my lines straight, but they really do fit pretty well with the curve, don't they? The same principle here applies as we talked about with those Riemann sums in regard to rectangles. How could I make this better? I could just do more trapezoids and make them really skinny, and more and make them skinnier and skinnier and skinnier. Eventually I'd have the exact area. We're going to just focus on the approximation, but in order to do the approximation, perhaps the most challenging part of the day is going to see if you remember what the area of a trapezoid formula is. Do you remember? Add the bases. I heard you say that. So B1 plus B2 times what? H over 2. Yep. So this comes from basically adding two triangular areas together. Like that's where you get this formula from. So you could write it as like 1/2 H times B1 plus B2. All the various arrangements. I suppose you could even distribute. I don't know that that would really make it any simpler. Whatever. You just do what you need to do. I think this is a good thing. So let's take a look at our example or examples. What am I going to do here? Let's at least do, I don't know about number 1 as much. Yeah, let's do number 2 for sure. Let's make sure we do this one. If we have time to do number 1, maybe we will. So it says a certain function f of x has the values in the table below. Approximate the integral from 2 to 17 using the intervals in the table and a trapezoid approximation. So I put in a little bit of repetition here. Do we go till 30?
Yeah.
30, yeah. Put a little repetition here, hopefully to help you guys get a little practice remembering that formula. I don't know how much you need as far as help goes, but you basically got a curve. We go from 2 to 3 to 5 to 8, so on and so forth. Yeah, 3, 4, 8, 17, so does something like that. What we're going to do here is we're going to build trapezoids into this picture by this and like that, so on and so forth. What's tricky about this in regard to the H's and the B1 and the B2?
The difference in the x's is your h.
Yeah, you should feel like the heights would be the height, the y values would be the height, but it's actually the x's, the difference in the x's that will give you the height, and the y values would give you your bases. So the trapezoid has been tipped up on its end essentially. So these would all be h's, these would all be bases. Almost rhymed. How about that? Okay, so for the first one, I would say, let's see, integral from 2 to 17 of f of x dx is approximately, it would be 1/2. My first height is only going to be 1 because the difference between 2 and 3 is 1. And then my bases are going to be 3 plus 4. Does it make sense with what you guys have? If it does, let's just let you run with it for a couple of minutes and see where you end up. I'll be around to answer questions. It is still a Monday morning, so who knows. So let's see here. The next one would be plus 1/2 times 2 times 4 plus 8 plus, the next one would be 1/2 times 3 times 8 plus 17. The next one would be plus 1/2 times 2 times 17 plus 13. Hopefully you're seeing all the good repetition here. 1/2 times 2, 13 plus 9. That's going to be 1/2 times 5, 9 plus 3. Good? So do you see how every single y value gets used twice, except for the first and the last? Should be that way. So let's see here. We've got 7.5 plus 12 plus, let's see here, 37.5 plus 30 plus 22 plus 30. What's that? Oh, 6.5, right? No, well, 3.5. There we go. Okay, so if we add up the 0.5 ones, 41, 53, 83, 105, 135? Good? Help me out. I got to stay sharp. It's Monday. I'm adding correctly. Okay, good. Okay, so 135, that's our approximation. There's no real way of knowing the accuracy of that as far as like, is it too high or is it too low? We don't really know enough about the function to know that. We knew the function was always, but we know that we don't know that it's either always concave up or concave down. That would be our justification for too high or too low here. Increasing, decreasing, I mean, we just don't know enough about it to know this. Okay. Okay, let me leave you with this. I hinted at this a few minutes ago. We're going to skip number one. Number one is pretty laborious. And in all honesty, if you're going to see a trapezoid approximation, it's going to be that, right? So I want to just challenge you. If you think about this in the next 24 hours, great. If not, that's fine. Cosine. We said that cosine was even. I'd like you to investigate this. We'll eventually come full circle around, and this will be a big thing in our class. I'm going to propose this, that cosine of x is approximately equal to, those are factorials, by the way. You get the pattern? You notice how all the exponents are even. And I would challenge you, like you can see this pattern here, if you were to continue it out of ways, out to like the 8th or 10th or 12th power, you would be hard pressed to find much of a difference between that polynomial and cosine. Especially if you kept your inputs around like close to 0, like 0.1, 0.2, or even like pi over 6 or something, you'd find that it's quite similar. And so one of the things we'll investigate this year is, why is that? Yeah, you see the even pattern, right? That would be a way to consider why is cosine even, because it fits that pattern still, even though it doesn't look like it at first. But we'll investigate where that comes from later on. I just thought I'd throw that out there. Food for thought. Have a great day. See you tomorrow.